Okay, good morning, everyone. And today, this tech talk, I want to talk about the FDIR and the Raman spectroscopy. And this FDIR and the Raman, I need to check that the Mary is still there. Okay. So I will start. So this FDIR and the Raman, this technique is most commonly used in the labs, in the analysis for chemistry analysis. And some students, maybe they know how to collect spectra for the analysis data still and have struggling and not fully understand the technique. Today, I want to take this talk to talk about the principle and hope to help you understand what is this technique, what is this information they can get. Okay, so first I'll talk about that is vibration of this. And talk about the molecular vibration, and then vibration spectroscopy, because both Raman and FDR is a vibration spectroscopy. And then we talk about the IR principle and the Raman spectroscopy principle and their comparison. This one. So both these techniques, they use light and interact with material. And the interaction between the matter and the light beam, they can be reflection, and then can be this transmission and absorption, and then scattering. And then based on this interaction, they can develop this different technique analysis. Like absorption, they can get the IR. Transmission also use this for IR. For emission, they can get fluorescence. And the scattering, and then get Raman spectra and reflection like optical microscope and the photoelectric effect and XPS, UPS like this, based on the interaction and develop these different and spectroscopy. And then the molecular vibration, that is definition is like a periodic motion of the atoms compared to each other. So this is the model of the Bose-Spring model. Is the atom and the spring, they are vibrate. Why they vibrate? This is because there's a thermal energy and a quantum effect. These atoms is oscillate, is continually, and at a certain frequency. And this vibration, the type can be stretching and bending and twisting. They can have different these vibrations. And why this is important here, we talk about this, because this vibration frequency is determined by the atoms, by the strength of the bond. If we can detect this frequency of the vibration, we know what atom is there, how strong the bond. And then that is the basis of the IR and the Raman spectroscopy. So they basically detect this molecular vibration. So that's why IR and Raman also called molecular vibration spectroscopy. So the stretch can be, and the vibration comes divided by stretch and bending. Stretch basically is the bond, the length change, and the angle not change. Like this, go this direction, and this symmetric, asymmetric, this length change. And the bending is the length is fixed, but is the angle changed. Here, this angle goes this scissoring, and this is rocking, and this is wiggling and twisting. And this is in plane and moving, and this out of plane is moving this. So this bending compared to the stretching is more variety, and that is more different type of this vibration. So this is like a movie, and like this show this here, this stretching, see this direction, and symmetric, unsymmetric. This scissoring, and this rocking, and this wiggling, and this outer plane, in plane. This one outer plane, one in plane, like this moving this. For IR spectroscopy, we use a broadband. This light, and shoot on this molecule. And then we know the molecule is a vibration. And then if this frequency not match to the vibration, and then this light will go through the path. Okay, sorry about this one. And the path. If this frequency is match to the vibration frequency, and then they will be enhance this and enhance this, get this vibration go to the higher level, and then this energy will be absorbed. And then here absorbed, get absorbed, the absorption peaks. And then this energy is passed. If this energy is mass to the bending vibration, the vibration, and then they will also absorb and get another peak. You see here, the IR spectrum basically is, that is, you get absorption or transmittance spectrum you can get, and basically this vibration absorbs the energy, and you get this spectrum. And then from the spectrum, you know which energy is absorbed, and that is matched to this chemical bond. So for talk about the IR spectroscopy, often talk about the dipole moment. What does this mean? And the dipole, I will know, that is like positive and negative center, and they have a dipole moment here, like this direction here. So if this vibration, if this vibration here is a stretch, if this stretch goes this direction, make this shape. You see here the dipole moment from here to there, the dipole moment changed. For this kind of vibration, IR is active, IR is very sensitive. They can measure this because this energy and IR energy is absorbed by this dipole moment change. And like OH, like carbon oxygen, like this dipole, they have a big dipole moment. And also when they are stretched, the dipole moment change, and then they have a strong peak for OH, carbon oxygen. But for this oxygen peak, they don't have a dipole. And during the stretching, also don't generate this dipole moment. No dipole moment change. And then use IR, you cannot detect this kind of chemical bond. And also cannot detect their vibration. So we know that IR detect the functional group and measure this vibration frequency. What is the vibration frequency determined by? So that is, we use a simple like ball spring models, and that follows the Hooke's law. Hooke's law there, the frequency determined by this is mu is a reduced mass, and this K is strength of the bond. And so for this bond is a carbon-carbon double bond, triple bond. This bond get the same element, same atoms. If the bond gets strength gets stronger, and their frequency get higher, and then wave number get higher than this. So this one also is surrounded by this bond, is get also can affect this bond, get this higher. If atomic mass, you see here carbon hydrogen, carbon carbon, carbon chlorine, yeah, carbon iodide. This bond, you see here, this mass compared to this one is much higher, and then we reduce mass higher, and then this frequency will be low, and the wave number will be low. So now, based on this theory, we understand why some and the chemical bond that is a higher wave number, some is a lower wave number. And so this gives you explanation about use Hooke's law. What IR can do, IR, this application, like this is the gold particle attached by the protein, by the polymer, by these chemical groups. And then we use IR, we can identify a functional group. If a surface attached on this group, we can detect. And if we do a surface coating, and they can do a surface analysis, they can see the thin film and the corrosion and the surface treatment, they can analysis. Is a polymer characterization, they can do the cross-link degrade, and this, you can see this and the surface. And then a qualitative and quantitative analysis, and then they can identify the unknown some compound, and they can measure the concentration of the compound in a mixture. So this IR spectrum, basically you can divide it to 4 different regions. For this region called a single bond stretch region, like OH, NH, like carbon hydrogen, all in this region. And this region, the narrow region, is a triple bond, carbon-carbon, nitrogen-nitrogen triple bond on this region. And the double bond, then the carbon-hydrogen, carbon-oxygen double bond on this region. On this region is a fingerprint region. We call the fingerprint because that is important for identify compound, but also that is complex, like a fingerprint, this region. And then we have a slide to talk about what is a fingerprint region, why there is so many peaks there. And then for the IR signal, basically, that is a more polar bond, that is give a stronger absorption, that is a higher intensity there. Like a OH compared to the carbon hydrogen, this is the more polar, that is the intensity will be much higher. And also for the bond, if it's symmetric, like this, both sides is same, the intensity is much lower. If it's this is end, here is the middle here, and this is asymmetric, their dipole moment change is huge, and the intensity also increase. So that the environment also affect this frequency a lot. So this is a glucose spectra we collect, use our instrument, use glucose. Here is OH, and the carbon hydrogen is clear, is less peak, but this region is fingerprint region. Right? Fingerprint region. And then for this, why is the fingerprint region so many peaks? First, let's talk about this vibration mode. We have a stretch mode and the bending mode. We know stretch mode is chemical bond is elongation and compression. This one requires higher energy. And for this kind of bond, and typically it's a higher frequency and higher and wave number on the left side of the spectrum for stretching. For bending, for twisting, and like rocking, this one just change the angle, not change the bond length. For this one require less energy. So that's why for bending, most on the right, the lower wave number, and this. And then that is for the bending and frequency, these peaks mostly go to the lower, like a fingerprint this region. Like here region, you can see the functional group above 1500 on this group. On the fingerprint, that is below 1500 on this region, fingerprint region. For that region, you mostly is the bending, wiggling, the rocking, this kind below this group. Why this group? There is so many peaks because at the beginning we also said for one bond, the stretching only one direction, maybe just one. But for bending, they can go bend different angles. They also can in-plane and out-plane. For a single chemical bond, they can have 3, 4, 5 different the bending vibrations. So that is a single bond. And one stretch, maybe they have several the bending, and that's why it makes the bending fingerprint region that is much more peaks. But if you have your compound, you have a different chemical groups, will make these fingerprints many, maybe more than 10, 20 peaks piled together across this area. Also, some is overlap. But for this region, is maybe difficult to identify each peaks, but for certain molecule, for certain compound, that feature is certain. And then this is why we call the fingerprint, like your fingerprint that you can ID what compound it is. We can use the software, we can use this and handbook to match, to identify what is unknown molecule, what is unknown that is compound based on fingerprint. So this is why this IR spec peak, and that is not fixed, that is changed so much. Some people maybe know XPS peak also they shift, but they shift very small. They just half EV, 1 EV, but the functional group they change so huge. Like here, the carbon hydrogen, this peak here, you see the multiple peaks also change a lot, like carbon, like here, because this chemical bonds is heavily affected by this chemical, by the chemical environment. Like this carbon hydrogen, and left is aromatic, this ring banded, and then they go here, and this aliphatic chain banded to this carbon hydrogen, and then they go this and this frequency. They are changed a lot. This also the different position they are changed, and so that's why. And this chemical bond and this chemical bond frequency, they are not fixed. They are shifted a lot by the chemical environment effect on this, and they can electronic effect like electronic donating withdrawing group. They can affect this. And then this hydrogen bonding and this bulk group, this can affect reduce the mass. If you use isotope, also can change the frequency. If you use a phase, for example, same material, if you use solid, use a gas, liquid, because the distance, the different, and then they also affect this peak position. So here I will give you a case, and this hydrogen terminated silicon. So you use this one, for example, in a clean room, you make this a clean surface, a hydrogen terminated silicon wafer, and then you should only detect this hydrogen silicon peak like the 2100. If on the surface you can detect this OH peak, carbon hydrogen peak, that means this surface is contaminated. If you can detect the silicon oxygen peak at 1000, means your surface get oxidation. So this kind of IR you can use like a quality control of your sample. Yeah. So we also have non-IR. So this is another example. This is on the silicon. You see a white spot. But you know, all this is a silicon white spot. Maybe that is contamination. And then you use another IR, this is 250 here. You get a spectrum from here, from here. From the blue spot, you see, so most of that is flat. Only here, a little bit noisy from like maybe silicon peak and bending, something like that. So, but here, no major peak. But for this part, you get a huge peak here. There's a carbon oxygen peak here. And then use this spectrum, you can search and match this, and you can find this. You find that it match to PET, and PET is commonly used for packing material for this semiconducting, or you know this silicon surface contaminated by the PET, and then you can use nanosims to identify this contamination. And this is a micro FDR, so that is micro ATR. You can do the mapping. This is an optical image, and then you can use the peaks and label this different and substance like this mapping. And in our lab, we have this and thermal nickelate, the IS50. This is for bulk sample, like for powder, for film, liquid. And also we have a Bruker Lumos and IR microscope. And we have also Bruker non-IR for the nanospot analysis. So we just talk about IR. We also talk about the Raman spectroscopy. Why we put together? Because Raman also detect this molecular vibration, and some chemical bond is sensitive to IR, but some is sensitive to Raman. So the Raman and IR, they called both molecular vibration spectroscopy, and also their information is complementary. So that's why, and I put it together. So this use laser to shoot on the molecule, on this substance, this your sample, and then they get the light. And most that is unchanged elastic scattering. And this is no energy loss and increase. And some, this is called the inelastic scattering. And this one, energy increase or decrease. This is a Raman signal we get. And for this laser, if you show the no energy change, this is called Rayleigh and the scattering. And this is very, very strong. And that's why in the Raman spectrum, you don't include the zero wave number, because that is basically the laser light in the Rayleigh scattering is very, very strong. You have to start from use a filter to remove this. And for this, mostly the molecular vibration at the ground level, if this laser and enhance them, get the higher level, and they absorb that energy, and then your laser light and get lose that energy, come out. That called as stochastics and the scattering. And this loose energy is this vibration, and that is a wave number, and you get the Raman spectrum. Some molecule already on the higher energy, on the elevated energy. If the laser shoot on this molecule, and then when the laser come out, they will take away this energy, and then let the molecule get the ground level. In this case, this laser get energy, they gain energy, and then this called anti-stochastic. And this is energy get higher, wave number get higher this. So for this one, and this rarely, and that is compared to stochastics, this is very, very small, and the fraction get this. Most we get this stochastics. So that's why you get the spectrum, and most that is positive the wave number. So this stochastic is much more higher than the anti-stochastic, but the really light is very high. Your fraction, your Raman signal only around the 10 ppm level, this fraction. So for the Raman, what do we detect? The Raman and IR, we detect the dipole moment. For IR, often talk about the polarizability. What this terminology means? This means this electron cloud, how they are easily to distort. And this example like this, and this and the fluorine and the iodide. For this fluorine electron is close to the nuclear, is tightly bonded here. And this electron cloud is not easily distorted. But the iodide in many shells, these electrons are loosely controlled by this nuclear. For this electron cloud, they are compared to this is easily to distort. So we say this molecule is a polarizability is high, this increase. Same thing like this. So this basically is a polarizability is like how stretching. If this electron cloud is easy stretching, is polarizability is higher. So we are for Raman, we are not just detect which one is easy, that is how they change. This is a chemical bond. This chemical bond, like before this electron cloud like this, after this stretch, change to like this and stretch like this. And this electron cloud compared to this one, so this is easier to distort, easier to change because they elongated here, this compared to this one. So this one, their polarizability is changed. For this kind of molecule, for this molecular vibration, Raman is very active, and then they can detect on this. Okay, so this and this bond. And another example is like this. If this bending here, this bending, even the dipole may be changed, but as a whole, the electron cloud not change. Like this one, this stretching, and the electron cloud not change, and the Raman inactive, they cannot detect. The only Raman can detect like this, and there is a whole electron cloud is changed, and then the Raman easily can detect. And the Raman, we also can see the Raman shift. And then on the lower wave number is a red shift, on the higher called blue shift. Why the shift? This molecular vibration frequency still use the Hooke's law. They based on the mass and the strength. If the atomic, these atoms not change, only strength changed. So for this red shift, that means you have a weaker bond. All bond, the length changed, increased, and the hydrogen bond affect this, or increase the mass, or increase the temperature also makes the red shift. For the blue shift, then there's a stronger bond, or bond shorten, or electron withdrawal group effect, or decrease mass, they can make the blue shift. So that is also there is a lattice vibration. What is lattice vibration? We know the single vibration, but for crystal, for crystal like silicon crystal, that is not the single bond is isolated. All the bonds that affect each other. For this, the Raman detect is not like a single bond. They detect as is a collective excitation, and this is called phonon. They detect the phonon. This is also called the lattice vibration. This lattice vibration compared to the single bond, that is a shift. For example, this for the silicon bond, that is individual is calculated, that is around like 400 wave number. For this lattice vibration, there is a whole, this collective vibration, that is 520. That is the huge the shift because it is a crystal that tightly bonded to each other that they affect. But for the molecular, and that is individually bound, they can detect. If it's amorphous or non-crystal, there's a between on this and their peak, and the between on this is a combination of this. This is a silicon here. If it's a crystal, you see here is the silicon is 520. And then if amorphous, fully amorphous, there is 480 of the peak here. If it's the middle like here, you can see this gradually, this peak going down and this amorphous going up. And based on this, if deconvolution of these peaks, we can get the ratio of the crystalline and amorphous of this. And use Raman, also you can detect like this MOS2, this different layer, one layer, two layer. And this is a in-plane vibration peak, and this out-of-plane vibration peak. If it is a single layer and no interact by the top layer, and then there's a gap is only 19 to 20, this distance. If they for the second layer, third layer, and then this will make this outer plane go to the blue shift and go to this in this in plane, and the red shift makes this gap is wider and get 21, 22, if bulk and get 25, and then this is based on the gap of the two peak, and then we will understand this layer is a single layer, a double layer as a bulk. And also is the same method we can use for the graphene and single graphene layer, double graphene layer. So another example is like strain stress. Also use Raman, we can analyze the strain stress. This is a gallium nitride sample. Gallium nitride sample, if we press this, and then we can see here, this ABC, this different position. A is makes the tensile stress there. The C is compressed. So for A point, this is tensile and the stress, and makes the bond is the distance, it get longer, length get longer, and then just the red shift and the frequency get is lower. And then get compressed, this region is C, and get a blue shift, and then get a bond is a short distance. And this use a shift, and then you can analysis this crystal or film. For example, if you make a film on substrate, if this is lattice affected by this substrate effect, make this strain and the stress, and then use a Raman shift, you can analysis this substrate effect. Also, you can do depth profile. This is because the laser you can focus. This sample is a silicon carbide, and the different layers they have a different the doping, and this nitrogen, this N doping, this aluminum doping, and this less doped. And because this doping and the concentration of free electron affect this peak, and these two peaks ratio is here, ratio changed, and then they can focus a different layer, and then see the peaks. And for this depth profile, use Raman, and then you have to, and your sample transparent. If it's opaque, you only can get less than 1 micron absorbed. If it's transparent, you can go more than 10 micron, go down this. And also Raman, you also can do the variable temperature and use minus 200 to 600 and 600. This temperature variable. You can see this example like lead dioxide. You can see the different temperatures, their phase change, and then you can see the peak, their change, and based on the temperature change. Also summary about the Raman spectrum. Based on the spectrum, and then you can see based on the peaks, you can see what is the peak position, you know what the composition of the material. It's based on the peak shift. you will understand if they have a stress of the material. And then if you change the polarization direction, I didn't mention on the previous slide, but our laser, we can put a polarization and the slide there, polarization and linear polarization, and change the direction. If your Raman intensity change, that give you information of your crystalline symmetry or orientation information, can get this. And then if your peak, you can see this Raman intensity, this width changed. And then this give you quality of the crystal. If amorphous is highly crystalline. And the intensity, and they give you the amount of the material. Of course, more material, intensity will be higher. Of course, you change the power of the laser, also intensity will be increased. So this for Raman spectroscopy, advantage is they can provide the chemical bonding information and analysis of solid, liquid, gas. And they can do depth profile, and they can offer in situ capability like temperature, environment change. And then you can, all special for Raman's aqueous solution is works. But for the IR is water solution will be very challenging. Disadvantage is this Raman, because the laser is very strong, they can cause the fluorescence can affect your Raman spectrum. And the laser induced material can degrade, then can burn your material. And then also they cannot provide elemental information, they only provide this chemical bond information frequency. And that is efficiency is not as high as like XPS, like top seams that is low needed, and the concentration is relatively high. Yes. So this is our system in our speed. We have this Oliba, the Raman system. We also have a TERS, tip enhanced Raman, and also have this heating cooling stage, and you can do in situ analysis. So for IR and Raman, you also can do quantitative analysis. What is the quantitative analysis you can do using IR Raman? So for IR, this intensity follows the Beer-Lambert law, and this absorption proportional to the path length, concentration, and this material, this. If you here for the Raman, this intensity also proportional to the laser intensity and the molecular concentration and the Raman cross-section of this. If you keep all the experimental conditions same, just change the concentration of this, you will see the intensity and the concentration is linear changed. It's like this example, and here, this spectrum and these peaks, we choose a strong peak, sharp peak, and then change the concentration, we can see the intensity, their change. And then draw a line, they follow the linear change. And then after you calibrate this line, and then if you have an unknown sample, use the same condition, you find use a peak area, you can follow this line, you can find this, what is the concentration of the unknown material. So we compare this IR and the Raman spectroscopy, and the light source use IR, use broadband mid IR. But for the Raman, we use a laser. We have 4 different lasers. Spectral range is for the IR is 400 to 4,000. And also for ATR, only start from 600. For the Raman, you can from the 50 to 4,000. If with better Raman, you can get even lower. With hours, you can get maybe 5 even here. The light interaction use IR is absorption, and Raman is inelastic scattering. And require for the IR, you require a dipole moment change for this and chemical bond. And for the Raman, you need the polarizability change of the chemical bond. For this, good for this polar bond like carbon, hydrogen, OH, this bond. And for the Raman is symmetric like this bond. For example, this IR most detect for organic and polymer is good at on this. And for Raman is inorganic, a carbon material. and accurate sample for the IR is very poor. And you want to analyze accurate solution, you need a very high concentration. And then that is because the water is a strong absorber, these huge IR peaks. And then for the Raman, that is Raman and water, Raman inactive, this is good. And the result is for the IR, you get a functional group identification. For the Raman, you can get a crystalline structure and the phase information and stress and the defect and the disordered information. And the Raman peak and IR peak, people always, when the analysis, want to click and get the information, get what that is. And probably they get a training for the XPS. XPS software that is smart. You click, they get the odd ID, they give you your peak table and they tell you what element on the surface. But for Raman, for the IR, you don't have that function, don't have that database. You have to be manually find the peak, find the peak position, find the handbook, find what peak it is. But now we have the AI. Seems this AI also, the free AI also can help to analyze spectrum and then identify the peaks. That is quite helpful. So I copied this spectrum in the OpenAI and then let them to analyze this FDR spectrum. They give me the list on this, and this broadband is OH, this is a sharp is carbon hydrogen, and this here, this peak. And then that is, I think that is not 100% accurate, but that is a very good start point and give you a lot of information. And based on this, you have to be, identify that is correct or some is maybe not accurate. And I think that is very helpful use AI, this tool. I hope after this around half-hour talk and you have a better understanding this Raman and FDR, what they works, what the information they can collect. And if you have a question, you can ask me now, or you can ask question anytime later.